Hello, everyone, and welcome to a crucial lesson in building robust, scalable systems. Today, we're diving into implementing data restoration from archives, essentially building your very own log time machine. In software development, collecting data is just half the battle. The real challenge often lies in making that historical data readily accessible and performant when you need it most. Think of Netflix's viewing history or Spotify's listening patterns. Users expect instant access to years of data, even if it's in cold storage. This lesson will equip you with the knowledge to deliver that seamless experience. By the end of this session, you will understand the challenges of historical data retrieval, identifying why it's more complex than simply storing data away. You'll also identify key architectural components for archive restoration, learning what essential pieces are needed for a robust system. We'll then explore real-world patterns for efficient data access, looking at how leading companies manage their historical datasets. And finally, you'll learn strategies for performance and cost optimization, ensuring your solutions are both fast and economical. Let's get started. The journey to building a log time machine begins by understanding the core problem. Many systems fall into the trap of treating archive data as a completely separate entity. This often forces users, or even other services, to know where their data resides. Is it live, or is it historical? This separation creates complexity, slows down development, and leads to a fractured user experience. Our primary goal here is to eliminate that distinction, to make historical data feel as accessible as live data. Imagine trying to analyze user behavior over 2 years, like a major music streaming service. You're querying petabytes of information. The sheer volume presents immense challenges, not just storage, but managing the cost of access and ensuring optimal performance. The ideal is a seamless user experience, where you can query years of data instantly from cold storage, just as easily as you query data from the last hour. This transparency is key to production-grade systems. To achieve this seamless experience, we need a robust underlying architecture. Let's look at the first two critical components. First, the Query Intelligence Router. This is the brain of your retrieval system. When a query comes in, the router analyzes its time ranges and content to determine the optimal data sources. For example, a query asking for errors in the last hour will naturally hit live data. But if you're looking for monthly error trends over the past year, the router intelligently directs that query to the archives. This smart routing prevents unnecessary archive access, saving both time and money. Next, we have the Archive Locator service. Once the router knows it needs archive data, this service steps in. It's responsible for mapping time ranges to specific archive files across potentially different storage tiers. Think hot, warm, and cold storage. Crucially, it uses metadata indexes to quickly identify relevant archives without having to scan entire storage systems. This quick identification is vital for achieving those sub-second query response times users expect. Building on our routing and location services, let's explore how the data itself is processed and brought together. First, the streaming decompression engine. It's a workhorse. It doesn't load entire large archive files into memory. Instead, it processes them in chunks. This is critical for efficiency and scalability, supporting various compression formats like gzip or zstd, and even decompressing while searching. Once data starts flowing from live sources and archives, the result merger takes over. Its job is to combine data from multiple sources into a unified result set, handling things like deduplication, sorting, and pagination across these heterogeneous datasets. The overall query processing states describe the journey, starting with query analysis, then archive selection, followed by parallel retrieval and streaming processing of data chunks, and finally, result assembly. To optimize this flow, we employ a smart caching strategy. This is often a 3-tier approach: metadata in memory, recently accessed archives on SSDs, and older data in cost-effective object storage. This balances performance with cost effectively. Now, let's look at some advanced techniques and real-world patterns that make these systems truly shine. First, compression-aware querying. Instead of fully decompressing an entire archive to search, advanced systems can actually search directly within compressed streams. This dramatically reduces bandwidth and processing for large historical queries, often by 80%. Next is temporal locality optimization. Users often query data from the last month, then immediately need data from last week. Recognizing this, the cache intelligently prefetches adjacent time periods, significantly improving cache hit rates in production. Another powerful pattern is progressive query execution. For very large time ranges, instead of making users wait, you present initial results immediately while continuing archive processing in the background. This provides instant feedback and a much better user experience. These insights, combined with the architectural components we discussed, empower you to build robust data restoration systems. You can now approach historical data retrieval with a clear understanding of complexities and solutions. To conclude, and for your self-assessment, how would you design a system to handle a query for data older than 5 years, ensuring both performance and cost effectiveness? Take a moment to consider the components and strategies we've covered.